So our second speaker is Pier Luigi Dragotti. He's a professor. He's professor of signal processing in the electrical and electronic engineering department at Imperial College London and a fellow of IEEE. Pier Luigi's research interests include signal processing, image analysis, image processing, sampling theory, in particular sampling theory, wavelet theory and its applications, sparsity-driven signal processing with applications in image super resolution, neuroscience, and field estimation using sensor networks. I think it's a fair thing to say, Pier Luigi, that a good part of your research in the last years has been also focusing on computational imaging for art investigation, some of which you will share with us today. Let me also say that if people want to hear more from you, you've also recently given a lecture at the Science Breaks event, which has been recorded and is available on your website and maybe somewhere else as well, but it's called When Art Meets Science. And I have been watching this. I can very highly recommend it. So yeah, but first to your lecture now maybe, but let me also say that Pier Luigi has been given various honors and awards for his achievements in signal image processing, including an ERC starting grant in 2011. He's currently editor-in-chief of IEEE Transactions on Signal Processing, a member of IEEE Signal Theory and Methods Technical Committee, and a member of the IEEE Special Interest Group on Computational Imaging. So you're very, very busy, and thanks a lot for leading so many initiatives in the field. Today, Pier Luigi will speak about when the Prony met Leonardo, on automatic algorithm for chemical element extraction in macro X-ray fluorescence data. Very much look forward to your talk, Pier Luigi.
Thank you, Carola. Thank you very much for the nice introduction. And thanks for inviting me to this workshop, very interesting workshop. I apologize for the convoluted title, but it encompasses everything, okay? So this talk is about some methods that we've used to analyze a painting by Leonardo da Vinci. And one of the methods that we use is known as the Prony's method because it's due to the Prony, and this will be more evident later on. This is work that we did jointly with the National Gallery, but I'll give all the credits at the end so that is also more clear. So first of all, okay, so museums and maybe the National Gallery in particular is getting more and more interested in doing technical examination of paintings. And so the first question is why they do that. And I would say that there are probably three main reasons why they do technical examinations of painting. First of all is to support historical, research so that one can interpret and contextualize the collections. So for example, they might be interested in understanding the material which is used in a painting so that they can better understand, for example, the working technique of the artist. And that can help also to address questions that might be related to attributions or maybe to find the precise timing of a certain painting. The second reason is that they need to, conserve and care of the collection. So this analysis helps them for this type of tasks. Because they need to understand how a painting changes over time. And it can change because obviously of deliberate intervention, maybe some form of restorations or some touches that happened over time. But there is also a question of maybe the painting itself aging over time. And so when we understand that, then they can understand how to preserve, obviously, better the painting. And obviously, the third reason is that through these techniques, one can create new unprecedented ways to present the collection to the general public. So to also better understand why we need to do these technical examinations, okay, let's immediately realize that when we think of a painting, we shouldn't think of it as a sort of a 2D object, okay? The painting is really a sort of a volume, is a 3D object. And in fact, if we could take a cross-sections of the painting, okay, we would see a stratigraphy, an idealized version of that is shown here. And so normally in the painting, you will have the canvas, then maybe you have some preparatory layers, then you're going to have maybe some sketches, some under drawings, and then normally you have several layers of paint. And why do we have several layers of paint? There are many reasons. First of all, obviously the painter brushes over and over the same regions, and so that creates layers. But obviously there might be other reasons. In some cases, there might be a painting underneath, or there might be just an evolution of the actual painting, the so-called pentimenti. So essentially, maybe a composition starts in a certain way, and then they need to change it for whatever reasons, and so they paint on top of that. So you end up having these several layers. And then obviously there is a last, let's say, layer of varnish to complete the painting. So let me show you a more realistic cross-section. So this is the painting The Virgin of the Rocks by Leonardo da Vinci, and that belongs to the National Gallery. The National Gallery took micro samples in the region which is highlighted here. And so through these micro samples, you can see the cross sections, which is shown here. And the cross sections then again show some sort of preparatory layer. There are some under drawings in this case, and we'll discuss about that a bit more later on. And then you have several layers of paintings. So that gives you a ground truth, essentially informations of what is underneath the painting, if you want, or all the layers in the painting, but it's obviously only on a small section. And ideally, we'd like to be able to do the same for the whole painting. Obviously, you cannot take micro samples everywhere because you would destroy the painting. Obviously, this is an invasive technique. So there is a need to have access to the entire information of the painting using non-invasive techniques. And that's why imaging has become, the non-invasive, standard way to do a non-invasive analysis. Originally, I would say most of it is done by using some specific radiations, like, for example, X-ray and infrared. And they already allow us to get some information about the painting on the surface, but also underneath the visible, which are useful, but it's still relatively partial information. And we'd like to be able to use techniques that can provide a much richer information for each, let's say, region or pixel of the image. In some sense, ideally, we'd like to be able to have really a signal produced by each pixel in the signal. And so a couple of techniques which are more popular now and which are used more and more often are hyperspectral imaging and XRF. And so I'm going to talk about XRF, which is the focus of this talk, so macro X-ray fluorescence. And so first of all, let me give you an idea of how that works. So the idea is that you have your painting, and then you illuminate a small region of the painting, let's call it a pixel, with an X-ray source. So you send pulses, a primary beam. And then what happens is that when you send that beam, then some electrons, which are in some shells of the atoms inside the elements of the painting in this region, will be ejected. Okay, so you are sort of you're sort of sending this source, and the consequence is that some electrons are ejected, so they create a hole. And so this hole is then covered by another electron, which is on a shell at higher energy. And so when the electron goes to a shell lower energy, then it releases some fluorescence radiations. And this is what we collect with a collector. So now these radiations are at specific energy levels, which depends on the on the atomic structure of the atom for which this is happening, which depends on the specific chemical element which is in this region. So what happens is that a specific chemical element will normally produce several radiations at different energy levels. So we'll produce a few pulses. And then you have several chemical elements, and so you end up seeing a signal which is really like a stream of pulses. And again, the location of these pulses is related to the chemical element, which is present on the surface of this region of the painting, but also underneath the surface, because this source can go deep. Okay, so we get these collections of responses, so this collection of pulses. And so really for one pixel, we get a 1D signal, which is a stream of pulses. And then the process is repeated by scanning the entire painting. So we analyze pixel by pixel. Each of these pixels produces a 1D signal, and then we cover the entire painting. So here is an image of the actual device, which is used by the National Gallery. So here is the device. So you point it to a specific point in the painting. And then, as I said before, that produces a stream of pulses like the one shown here. And then, as I said before, you move the device gradually so that you scan the entire painting. Here is another example. Okay, here I took an image of a painting which we are more familiar with, I would say. So this is, let's say, one of the sunflowers painted by Van Gogh, and this is the one that belongs to the National Gallery. And then you can still see the device here in action. Right, okay, so if I put everything together, as I said before, so you have your painting, you illuminate one region, and that will give you a 1D signal. Therefore, when you repeat the process for the entire painting, you get a 1D signal for each of that. So you end up with the volumetric data sets like the one shown here. So we have this data cube. And what we'd like to do is to extract, as we said, to localize where these pulses are so that we can work out the chemical elements which are present in the painting. And so we would like to produce chemical maps of all the chemical elements present in the paintings. Now, what we have, first of all, is a table that it tells us what are the energy level expected for each chemical element. Okay, so here are a few examples. So just to give you an idea, it's not that this is real, but imagine that we have bromine, okay, for example, in our painting. So then that would produce, for example, a pulse at around this level, which might be, for example, this pulse here. But the same chemical element may generate another pulse, okay, as indicated here. And so maybe that might be this pulse here, okay? So you could get a few pulses related to a single element. And then maybe these other pulses that we are seeing here might be due to different chemical elements, okay? And the localization of the pulse is what allows us then to work out the energy level and therefore what is the chemical element that is related to that pulse. The process of, let's say, disentangling this information from the data cube is known in the art investigation community as deconvolution. Normally, we use the term deconvolution to mean something else, but that's to clarify that. And so to give you visually an idea, you have this data cube, and then this is what we'd like to extract. So these are the chemical maps, okay? So the quantity maps of some of the chemical elements which are extracted in this painting. So our goal is to try and perform this deconvolution process in a fully automatic way. Most of the current methods normally require some form of user intervention. And instead, we want to do that completely automatically. And so we need to automatically localize the pulses, as I mentioned before, but also work out the right number of pulses. And then once we've done that, we need to link them to the correct chemical elements. So map them to the correct chemical elements so that we can then extract the chemical maps. There are several difficulties in doing that. So first of all, many pulses are produced and they tend to overlap. The reason is that, first of all, a general pigment would contain many chemical elements, so each of them produces pulses. But the other reason, as I mentioned before, is that, remember, we have several layers of paint. And since the XRF, the beam can go deep, we get a response from all these layers. And therefore, we end up getting several pulses which are mixed together. And it's quite critical to be able to separate overlapping pulses, because if we see, let's say, something that looks like a big pulse and we decide it's a single pulse, we may be missing some important chemical elements if that pulse is in reality a combination of several pulses. So being able to separate overlapping pulses is an important issue. The other problem is that these pulses have a huge dynamic range. So if a pulse is related to a chemical element, for example, on the surface of the painting, and maybe it's in big quantity, then you're going to have a very high response. The response is essentially the number of photons that we collect, and you can have maybe 400, 300 counts. But at the same time, you can have very weak pulses, either because the chemical element is present in small quantity, or because it's a response coming from something which is underneath, so below the surface, and therefore this is severely attenuated. So we have this issue of being able to locate large and small pulses, and the small pulses could be really buried in noise, and so there is a difficult decision on whether what we're seeing is just noise or is really a small pulse. The last thing is that, as I mentioned before, normally a chemical element would produce several pulses, and we know what are the expected pulses. However, the relative amplitude of the pulses is not a reliable information we can use in our estimations, because that could depend a little bit on where the element is in the system, because obviously there can be secondary effects or some form of shielding and attenuation that can happen, which is going to affect the amplitudes in different ways. So the fact that we cannot really rely on the amplitude of the pulses related to the same chemical elements means that we cannot treat this as a simply classification problem. And so our approach, as will be evident in a second, is to localize the pulses first, and then based on that, essentially decide which are the chemical elements which are present in the painting. So that's an overview of our method. So the input, as I mentioned before, is this data cube. Then we have some pre-processing stages, which are not that relevant here, at least. It's a sort of calibration stages that we need to perform. And after we have done that, we first try to localize the pulses and detect the right number of pulses. And here we use an approach which is based on a framework which we developed in the past, which we call finite rate of innovation theory. And I'm going to describe that in detail later on. And then once we have detected the pulses and localized them, then we need to assign them to the chemical element. And when we do that, we produce two maps. One is the quantity map. So that is going to tell us how much of a certain element is present. And the other is a confidence map, which essentially tells us how confident we feel that that element is genuinely there. Okay, so this will give us a number between 0 and 1. 1 means we are very confident that we generally found something which is that element. Otherwise, it means that maybe we found something, but might not be that element, might be noise or something else. One of the advantages of the confidence map is also that it essentially normalizes things, by definition. So it gives you an image with a range between 0 to 1, which for visualization reasons can be very useful, because as I mentioned before, the quantity map, there might be a huge dynamic range. So sometimes it's not that easy to visualize these maps, because some region might be so bright that you need some manual intervention to make the other regions more visible. Okay, so how do we do these detections and localization of pulses? So, okay, we operate pixel by pixel. And so a signal in one pixel is a signal like the one sketched here. Okay, and so as I said before, it's really a sum of pulses. Now we know the shape of the pulse, phi. Normally it's a Gaussian pulse, but essentially we know it, and we can estimate, for example, the variance of this Gaussian. So the shape is known a priori. And so we can think of this signal as a signal like the one shown here. So it's a sum of pulses. The location of the pulse, Tk, is related to the chemical elements that we are considering, whereas the amplitude of the pulse is essentially related to the quantity of that element. And so really the question for us is, given our signal, which is yn, how can we retrieve this set of parameters, so the Tks and the Ak? Okay, so it's a sort of parametric estimation problem, if you want. And as I said before, the Tks are important to work out which chemical element is present, and the Ak are important to allow us to work out the quantity map. Now, the estimation of the location is a nonlinear problem, whereas the estimation of the amplitude is a linear problem. Why is that? Because if you have two signals, they are both stream of k pulses. If the locations are the same and are fixed, if you combine them linearly, you still get a signal which has k pulses. So the problem is linear. But if you combine two arbitrary stream of k pulses, you normally end up with a new signal with 2 times k pulses. And so the location leads to a nonlinear type of situation. So estimating the location is obviously much harder. So our idea is to connect our problem to a method which is broadly used in engineering, actually, which is known as Prony's method. And that's because it was introduced by Baron de Prony in the late 18th century. Obviously, it was solving something different than this, but is a method that then has evolved over time and has been used in many different contexts in engineering. And in order to do that, what we need to do is, given our signal yn, so remember yn is this stream of pulses, we need to convert it in a new signal, which I'm going to call SM, and this is still a sequence, okay? It's a discrete sequence, which must have this shape here, okay? So it's like a sum of exponentials, UK, okay? M here is a whole number, is an integer, okay? And ideally the BK here, so the amplitude here, is related to the amplitude of the pulses that we're trying to estimate, whereas the exponential is related to the location of the pulse, okay? So the idea here is that if I can convert this yn into this other sequence, which has this shape, then this signal here can be fed to Prony's method, and Prony's method will essentially automatically estimate, produce the BK and the UKs, and therefore will give us the parameter we are after. So that's the idea. Now, from this shape, you can still realize that finding the UK is a nonlinear problem, right? There is a power m here, okay? Whereas if I know the UK, finding the amplitude is a linear problem. So how do we do this connection? So we achieve that by essentially doing the following. Remember, phi is the shape of the pulse and is known a priori. So what we'd like to do is to find linear combinations of uniform shifts of my phi, such that when I combine them, I approximate a specific function, which in our case must be a complex exponential. So the question is whether I can find these coefficients such that this equality is satisfied. Now, among the exponential I need to approximate, okay, we need to make sure that the frequency here that I pick are evenly spaced. So is of the form omega 0 plus m lambda, where omega 0 and lambda are arbitrary numbers, but m is an integer, okay? And why I need evenly spaced, the frequency will be more evident in a second. So the first question is, can I do that, okay? So can I approximate a complex exponential using uniform shift, a linear combination of uniform shift of my shape phi? Let me show that to you visually, first of all. Okay, so here is the shape. Okay, so the idea is that I take this shape, there will be one of these black lines here, I shift it uniformly, and then I make a linear combination, so it's a weighted sum of all these shifts, okay? And that's, you can see here visually, then this sum gives me this signal here, which is clearly very close to a complex exponential. Obviously, I'm showing here the real part of that, which will be an oscillating cosine wave, but we can see that it is quite close. Okay, and so the idea is that I find these coefficients so that I can reproduce a certain exponential. Then I change these coefficients, and my hope is to be able to reproduce a different exponential, maybe that oscillates an exponential that oscillates a little bit more quickly or a little bit more slowly. Okay, so the question is, can I make sure that this sum here is sufficiently close to a certain functions fmt? And for us, close means in the least squared sense. Okay, and so since we try to do that in the least square sense, really what we're trying to do is to compute the orthogonal projections of this function into the subspace, which is covered by the prototype pulse phi and its uniform shifts. Okay, so because of that, then we can directly rely on the orthogonality principle in the projection theorem to work out the coefficient Cmn. So the idea is to find the coefficient such that the error in my approximation is orthogonal to the subspace onto which I'm projecting, okay? Because we know that the orthogonal projection has to satisfy this condition. Now, this leads to a set of equations, and then based on this set of equations, we can find the coefficients. Now, since we are in a specific situation, so we are trying to reproduce an exponential, a complex exponential here, then actually we end up with a closed form expression for these coefficients. The fact that we use the complex exponentials essentially turns integrals into Fourier transform, really. And so that's why we end up with a closed form expression. And it turns out that these coefficients are, first of all, discrete time exponentials. So if I'm trying to reproduce e to the j omega mt, I end up with the discrete time exponential e to the j omega mn. And then there are some coefficients here which are essentially related to the Fourier transform of the function phi, and then to the Fourier transform of what we call the deterministic correlation of the function phi with itself. And in both cases, the Fourier transform is evaluated at the specific exponent that I'm trying to, at the specific frequency that I'm trying to reproduce. Right, so given these coefficients, then essentially we are able to do the mapping that we wanted to do. So the way we achieve that is now quite simple. So given the signal yn, we compute these linear combinations with this coefficient CMN, which we found before. And remember, this coefficient only depend on the shape of the pulse, which we know, okay? So given these coefficients, we compute this weighted sum. Now, if I replace y with its expression is a sum of pulses, and then I change the order of summation, then this quantity here by constructions is approximately equal to the complex exponential, which is here. And then since these exponentials are evenly spaced by construction, then this sum here ends up being exactly equal to the sum of exponentials that we can use with the Prony's method. So just to summarize, okay, once I found the coefficient CMN, what I do is we get our signal yn, we compute these weighted sums. Remember, there are different weighted sums because I can change m to reproduce different exponentials. So each of them is going to give me a new number as m. So this is really a sequence of values. And this sequence of values actually is really equivalent to this sum of exponentials, which we are now going to feed to the Prony's method, and Prony's method will spit out automatically the locations and the amplitude. So the Prony's method will give us the U case and the V case, and then from there we retrieve locations and amplitude of the pulses. Let me give you a very quick overview of the basic idea of how Prony's works. Okay, so remember we have this sequence here, which is the sum of exponentials. Now, sum of exponentials are solutions to linear differential equations, okay? And in fact, since here we have something discrete, okay, these are solutions to difference equations. And we know that when we solve this type of equations, we use the so-called characteristic polynomial. So the idea here is to think in terms of the characteristic polynomial, which is really the polynomial whose roots are actually the exponential that we're trying to retrieve, okay? Now, we don't know this polynomial yet, because obviously the roots UK is exactly what we're trying to find, right? But if we know that there are k pulses, then we know that this polynomial is a polynomial of degree k. And so the coefficients of the polynomial are, let's say, h1, h2, hk, which we need to find. But then what is interesting is that if you take these coefficients here and you think of them as a sequence and you convolve this sequence with Sm, which is the sequence you have, then you can verify that that sequence is exactly equal to 0. Okay. So in engineering, we call these H's, we think of it as a filter. We don't think of it as a polynomial. And so this is a filter which sets to 0 the signal. So we call it the annihilating filter. Okay. But obviously in maths, people are more familiar with polynomials. And so this is known as the Prony's polynomial. Okay. But now the fact that we know that when I do these convolutions, I get 0 allows me to write that convolutions in matrix vector form. So here I end up with a matrix which is made of the elements S, which is something we have, right? So this is what we know. And this matrix is toplets because it's a convolution. And then we know through this expression here that when I multiply it by a vector whose entries are the coefficients of my polynomial, then I get 0. Okay, so that means that the coefficients of this polynomial are in the null space of this matrix. Okay, now this matrix is normally of size k times k plus 1, and it is full row rank. So the null space has dimension 1. So that means that this vector is unique. Okay, so that's the idea behind Prony's method. So algorithmically, then it's easy to solve the problem. So you have your sequence S. You generate your topless matrix T of size k times k plus 1 at a minimum size. And then you look for the singular vector related to the 0 singular value. Okay, so you do the SVD of T, and then you pick that singular vector, that will be H. Now, given H, you create your polynomial X, the Prony's polynomial, and then you look at the roots of that polynomial, and that will give you the UKs, so the exponentials. And once you found the exponential, then finding the amplitude is then trivial because it's a linear problem. So that's the basic Prony's method, which allows us to solve this problem. The more I see it, the more I'm fascinated by it, because again, this is a nonlinear problem, right? And the fact that you have 2k unknowns and you can actually solve it with 2k equations is in itself remarkable, okay? And the solution is unique, obviously, if the UKs are different, okay? So it's quite remarkable in itself. But anyway, that's the basic method. Over the years, there have been evolutions of these methods, so to make it much more resilient, for example, to noise. So some evolutions are known as the matrix pencil method, Esprit method, Kazao routine, and so on and so forth. And this is what we normally use in practice because they allow us to achieve the same goal but in context where the signal has a lot of noise. Right, so far so good. So remember, we started with our signal yn, and thanks to Prony's method, we can retrieve the locations and the amplitude of the pulses. There is a little catch here. The issue is that Prony's method requires to know a priori the number of pulses that we're trying to retrieve, so the number k, which is something that in fact we don't know. For us, k is an important parameter because essentially it tells us how many elements are present in the painting. And so we need to estimate this k. So the way we do that is we leverage the fact that Prony's method is very fast. It's based on algebraic manipulations, really. And normally these matrices are not that big, so it's a relatively fast method. And so what we do an exhaustive search. We start with small k, and then we gradually increase k. And then we re-synthesize the signals that we obtain and try and see whether what we get is consistent with the physics of the problem and is also a good approximation of the actual data that we get. So essentially, we expect that our result will produce pulses with positive amplitudes because all the amplitudes are positive, but also the error that we have when we approximate our original signal with this stream of pulses has to be sufficiently small and essentially similar to the energy of the noise, which we know because we can estimate. Because the intuition is that once I achieve that, once I find a k such that all the pulses are positive and the error is really has an energy similar to that of the noise, we don't need to find another pulse, because when we look for another pulse, then what we're starting to do is to reproduce noise rather than retrieving the signal. So that's why we stop at that point, and that gives us a good estimate on the number of pulses. Okay, so now we have detected hopefully the right number of pulses and then located them, and we worked out the amplitude of the pulses. So you can think of those as these sort of red arrows here. So some are larger, some are smaller. And now we need to assign them to the correct chemical element. Remember that the chemical element produced are related to specific elemental lines. So you could have some lines like the one sketched here. Maybe these are related to different elements, okay? And so I need to decide whether, for example, this pulse that I have located here belongs to this element here. Now, since our estimation is done with noise, there is always an error. So we need to have a certain tolerance. And our idea is that we want to have a bigger tolerance if what we estimate is a small pulse, because it's more likely that the location that we estimated was not that correct. Whereas we want to have a smaller tolerance when the pulse has a larger amplitude, because we expect that our estimation should be very reliable. Okay, so based on this tolerance, then essentially, based on the tolerance, we check whether our pulse is sufficiently close to a specific chemical element within that tolerance. So here, this small pulse is maybe a little bit far away from this guy here, but since we have a bigger tolerance, we still assign this pulse to this chemical element. On the other hand here, for example, this big pulse, okay, has a much smaller tolerance, so maybe it's not that far away from this element, but for us, it's not sufficiently close, given the fact that we have a small tolerance, and therefore we don't assign it to that chemical element. The open question is how to decide this tolerance. Okay, the intuition is clear. If the pulse has a lot of has a big amplitude, then we want a smaller tolerance. Otherwise, we want a large tolerance. The question is how can we systematically decide how to change that? We do this using essentially Kramer-Rao bounding techniques, because remember here what we're doing is really a parametric estimate. We are solving a parametric estimation problem, and Kramer-Rao bounds tells us how the best possible performance we can achieve. And so really that tells us what should be the minimum possible tolerance according to the signal to noise ratio that we are seeing. So what we do here, we compute the Kramer-Rao bound for this type of problem, which is what is shown here in blue. And the red line is actually the performance of our algorithm on a synthesized pulse. And so we follow the Kramer-Rao bound performance. We don't achieve those, which in some sense is not surprising, but we follow that behavior. And therefore we can use this curve as a curve that can tell us how should I increase this tolerance according to the amplitude of the pulse. And so based on this curve, we work out this tolerance Tk, and then we do the assignment, as I mentioned before. So imagine that this is the pulse that we found, and this is the chemical element. So based on how far the chemical element is to the pulse, then we assign the confidence score. The closer, the higher the confidence score. Whereas in terms of the quantity, we assign directly to that element the amplitude of our pulse as quantity. Okay, so that sort of completes the whole algorithm. First, we estimated the locations of the pulses and their amplitude, and then we assign them to the chemical elements using in part these camera bounding techniques. So let's sort of look at some results, something more visible. So first of all, let's look at the case of the sunflowers from Van Gogh. Again, this is the painting that belongs to the National Gallery. This is the region which was scanned by the National Gallery. And then they gave us the data sets, and then we run our algorithm on that data sets. And so here I give you some examples of the chemical elements that we've been able to extract. And then obviously the curator can, and the expert can analyze these chemical elements. For us, or at least for me, was not really an expert, but for example, this indicates that the yellow region here, for example, contains a lot of zinc, etc. Okay. But definitely what was more interesting is when we ran our algorithm on this specific painting, The Virgin of the Rocks by Leonardo da Vinci. So let me first of all focus on this region here. Okay, so this region again, I mean, the whole painting really was scanned using a Bruker instrument, which belongs to the National Gallery. And so the National Gallery gave us the data. And so let me focus on this panel first, and let me show you two chemical elements that we extracted. So the first one is the copper, and it will be more evident in a second why this is interesting. But anyway, so our system produces a confidence map here and the quantity map, which is shown here. And what you can see here is that, for example, there is a huge quantity of copper in this region here, which is a drape, which is present here. Okay. But definitely what is more interesting is when we extracted the zinc map, because from the zinc map, this is the confidence map and the quantity map. And then you can clearly see a shape, okay, of an angel. Okay, so I think you can clearly see the wings of the angel, for example, here, and the head of the angel. And if you're good enough, you could also observe here, there is the head actually of Christ. Now, if I compare this zinc map with the visible image, clearly we cannot see the angel anywhere. So that's clearly related to an underdrawing of a previous composition that was then abandoned. The National Gallery was already aware of this, okay, and they were already able to extract this type of a map. But our algorithm, as I'll show in a second, is able to extract this with much more clarity and also way more consistency across the various panels. So let me focus on two pixels here, pixels A and pixels B, to sort of analyze our algorithm, okay? The first issue is that if you look at the chemical lines, okay, the copper and the zinc, at least the main lines of the zinc, overlap or is very close to a couple of lines due to copper. So that's why I showed the quantity map of the copper. Now, if I look at the pixel A, okay, we know that there is, visually, there is some zinc here because the zinc is related to the wing of the angel, okay? And now, if I look at the XRF data for that pixel, only in the region of interest, so this is the type of signal I see, okay? And so you can see that there is a pretty large, a relatively large pulse related to copper, because there is copper in this region. And so we find it. There is the second line here related to copper. This is much smaller, but there is this line here. Okay, so the difficulty is to see whether there is a line here or whether there is noise. Because if you look at the counts here, okay, so the number of photons that we have here is really 5, 6 counts, okay? So it's extremely small, and it's really could be noise, right? But the algorithm decides that there is a zinc here, so finds the pulse here. And visually, by inspection, we know that that's the correct call, because obviously is the zinc here related to the wing of the angel. So we clearly realize that this is correct. Now, the pixel B is probably less exciting from a visualization point of view, but it's actually quite interesting from an algorithmic point of view. So if I look at the pixel B, so this is the signal here, okay? Now, this is on the drape, okay, that I mentioned before. And here, the copper is in huge quantity, okay? So if I look at the XRF data here, you can see that the two pulses related to the copper now are way bigger than before. In fact, here I cannot show the whole pulse, okay? The count is probably 400, so it's a huge pulse here. And then there is this other pulse, the second one, due to copper, which is also very large. Now, what is interesting is that the algorithm decides that this small, variations here is actually a pulse, okay? It's a small pulse covered by the big one, and is related to zinc. Okay, so our algorithm consistently finds small quantity of zinc in this region here. Okay, and already visually it's a little bit difficult to decide whether that's correct or not. But also other techniques will not be consistent in deciding whether zinc was present there or whether zinc wasn't there. So it wasn't really clear whether the zinc is there. But actually, the National Gallery has taken a cross sections in that region, and the cross sections has shown the presence of the zinc, which is for us quite remarkable because that indicates that our algorithm, decided that there was this small pulse here, and it was actually correct. Okay, so we ran the algorithm on then other panels, okay, of the painting. So you can see the panels here against the visual painting on this side here of the slide. And here you can see the zinc map for the three panels. And first of all, you can see how the algorithm is very consistent. Okay, the type of results that we get is more or less the same, even though the algorithm operates independently on each of the panels. And then you can see, more interestingly, probably, that actually there is a much more complex composition here. So this is the angel that we were discussing before. This is Christ, and this is the Virgin. Okay, and if you compare with the actual composition now, you can see that this is completely different. I am an engineer, so I'm not an expert in art, obviously, but the curator made me notice that apparently, if you look at the original composition, it seems like Christ and the Virgin are looking at each other, whereas in the current composition is the Christ and John the Baptist that looked at each other. So that would suggest that maybe originally Leonardo had probably a completely different message in mind and completely different compositions, and then he decided to do instead something different and change the sort of focus in the composition. Obviously, I think that's something quite interesting, but obviously it's something for the art curator to analyze and to explain to us. But I thought it's an interesting thing that would be nice to share. Okay, so I think I can conclude here. I think this is a meeting about maths for art and science. So it's the meeting between art and science. So I did my meeting, okay, between art and science, or art and maths, because I sort of combined two great, artists and scientists of the past. On the one side, we have Leonardo da Vinci, which is obviously doesn't need an introduction, is very well known. But on the other side, there is Gaspard de Prony, which is these French mathematicians and engineers, which I learned to love a lot over the years because I used this algorithm many, many times. But he's a remarkable, scientist in his own right. I always like to remind people that there are 72 names engraved on the Eiffel Tower of great mathematicians and scientists, and de Prony is one of those. So it's really someone who did remarkable work for the maths and for engineering. And so to me, this project is also nice because it is really, two giants, okay, of the past that meet. And also it's again an inspiration, I think, for all of us, because really when people, do something remarkable, right, then we always rediscover what they do. We always learn new things, and they always help us to break new barriers. And I think that's a great lessons, I think, for all of us. Okay, let me just conclude by saying that this specific work that I presented is joint work between Imperial College and the National Gallery. At the Imperial College, the work was done by two students of mine, Su Yan and Junjae Wang. The collaborators at the National Gallery are Catherine Igitz and Nathan Daly. But this is also work which is part of a broader project led by UCL, which involves also the National Gallery, Imperial College, and University, and is sponsored by EPSRC. Thank you very much.
Thank you very much, Pier Luigi. A wonderful statement to finish your talk. Thank you very much. That was really inspirational. Questions? Simona, you seem to want to ask a question.
There is a question in the chat, possibly.
Yes.
As the priority.
Yes, Elizabeth, do you want to ask your question yourself? Can you unmute yourself? Or Ale, do we need to unmute Elizabeth? Or
I will
ask to unmute. Okay, I think I can do it.
She say.
I know she's in the library. And can talk.
Okay, fine.
All right,
okay.
so I'll read the questions, okay? And that's
Yes.
one of the typical questions I don't think I can answer. So she asked, I'm curious about the identification of the pigment as zinc, as I was under the impression that zinc white wasn't commonly used until the 18th century. Is the drawing a metal point using brass? Okay, so yes, so I guess the expert can answer this precisely. Okay, so we extract the element, okay? So we know that there is the zinc element. Now, what is the pigment related to that is something, I mean, personally, I don't know. In general, it's not that automatic to link a chemical element to a specific pigment. I think we believe that the underdrawings are probably ink, so it's really, you know, an underdrawings. But it might be something that then was painted actually over, so it might be brushes. I don't think that's clear. I don't know whether this is white zinc. It's not the first time I was asked these questions. I don't think it is white zinc, but the curator knows way better than me. The other thing I can say is that zinc is one of the elements that was found. Then there is iron that was found for sure. But I don't think I can provide a precise answer of what pigment that one is. Let me probably just add one thing, is that there is a technical bulletin that, let me probably stop sharing my screen. Before I do that, okay, let me probably just do one thing. Here are some references. The technical bit that I explained has been already, you know, published in a short version in a conference paper. We are producing a journal paper more comprehensive, which is this one here. The more, you know, view from an art curator point of view of Leonardo and all the aspect of that painting can be found in this bulletin of the National Gallery, which will appear very soon. And I think probably some of these questions, I don't think there is a clear answer, but probably there will be more insight about the answer to these questions in that technical bulletin. Unfortunately, I haven't read it yet, so I cannot, I don't know, provide you, you know, any information about that, but it's forthcoming, and I really recommend, I mean, if you're curious to read it, I think it's a very interesting thing, you know, this analysis of Leonardo's painting. Okay, so let me stop sharing, and then, yeah, if there are other questions. So from the chat, okay, so there is Catherine Igitz, who is the expert from the National Gallery. She provided an answer here. So we think that the zinc is the underdrawing, in the underdrawing is a minor constituent in an iron gold ink applied with a brush to create the underdrawing, okay. Instead, the zinc that we found in the drapery, okay, is a minor component in the copper-based azurite pigment. Okay, so that's, I guess, as precise as we can be.
Suzanne, do you want to ask a question?
Yeah. I was actually just going to talk about ink, so it's answered. That's lovely, thank you.
Right. I had a more technical question, Pier Luigi, about the Prony method. So you said, because you don't know the K, the capital K, you need to find out what the good capital K is, right? What the most appropriate is. So how much, I mean, this is, I guess, one of the overheads of your of your approach, right? Because you have to apply the Prony therefore several times.
Yes.
So could you say maybe a little bit more about how often you need to do this usually?
Yes. Okay. Well, that's a good question. So in the results that I showed here, we do that pixel by pixel. Okay. So we do this sort of exhaustive search, if you want, pixel by pixel. Now, since the K is relatively small, okay, and we start small and go and grow, right? Then is the most effective way to estimate the correct number of pulses. There are other techniques that can be used. This is a model order selection problem, but we find that this is the most robust way to do that. Now, if we do that pixel by pixel, as we are doing in this case, then we pay a price in complexity. Okay, so it takes a while to extract the elemental maps. We are now exploring ways to do that either in a sort of multi-scale way. So you do that on a bigger block, and if you need it, you reduce that. Or actually, we do only once on the entire painting. So all this process, and then we sort of adjust it, let's say pixel by pixel, so that we end up with something which is very fast. Preliminary results are good in the sense that we end up with performance similar to the one that I have presented here, but obviously we are then much faster, but we are still not as good as what I've shown. Okay. So that's a good problem. And at this stage, our priority has been, efficiency, robustness of the algorithm. So to make sure that we really find all the things which are correct without worrying too much about complexity.
Yeah.
Just to give you a ballpark, right? So I think we do each pixel in a fractions of seconds, okay? This is exhaustive, right? But obviously these are big paintings, okay? So when you multiply that for all the pixels, then it takes hours, okay? But the algorithm itself is relatively fast because, as I said, K is not that large, it's manipulation of matrices, and so it's actually relatively...
It's really the number of pixels that you have that makes it heavy, but you're not under time pressure anyway, I guess, with these kind of applications.
No,
so.
absolutely.
Yeah.
I mean, we would like probably, definitely people would like to get results in order of minutes, I think, so that they can sort of, see, and rather than several hours. I think our method, this takes probably 10 hours for the whole painting. So we definitely need to reduce that, but definitely we don't need real time. Absolutely.
Yeah. I find the Prony's method, which I got to know through you, Pier Luigi, actually, quite fascinating. So it's really, really powerful. Yeah. Do we have other questions? Simone?
I have a question mainly related to the requirement of equally spaced points, and probably I missed this thing. Is it related to the fact that it is similar to the fast Fourier transform? Because I have in mind that there exists the non-equispaced fast Fourier transform. Possibly you can sample the points close to your relevant peak and forget about the rest.
Yeah, so, okay, I guess there are a couple of things here right? So one is the frequency that we reproduce, okay? We need them to be evenly spaced, not because of the Fourier transform in some sense, but because when we have this sum of exponentials in Prony's method, you have UK to the power m, okay? And m is a whole number so that you have like a sequence, okay? And then the problem is normally discrete time, okay? Otherwise, you cannot solve it, okay? I mean, there are probably iterative ways to solve it, but so this is why we need the frequencies to be equally spaced, okay? So that we end up with this SM, which is like a uniformly spaced sequence, and then you can do convolution, end up with the matrices, etc. Now there is another bit which is evenly spaced, okay, which probably I sort of went through very quickly, which is the pulse phi. When we do the linear combination, the shifts are uniform, okay? Now, again, we can, allow non-uniform shifts, but then the problem is complex and there is no closed form solution. So the fact that the shifts are uniform really allows us to play with the Fourier transform, etc. So it's what people would call, you know, shift invariant subspaces. Okay, so it is really helpful to have this shift invariance because makes all the mathematics behind the derivation much simpler. Okay.
Thank
And
you.
so
Thanks.
we need both. Okay. Yeah.
Thank you.
So thanks a lot, Pier Luigi. Thank you very much. Thanks a lot, Pier Luigi. Thanks a lot, Jean-Michel. Was really, really very interesting, and also two very different perspectives on how to combine art and mathematics, cultural heritage and mathematics. So I think that was really giving us a wide spectrum of the different interactions that we can have